So he's an associate regional director at GluMac, where for the last 8 years, he's worked with architects, owners, and on-site facility managers on identifying the energy and water usage goals of a project's design and to optimize sustainability, affordability, and architectural design. Michael has a mechanical engineering degree from Cal State Polytechnic University, Pomona, and he is a lead accredited professional in building design and construction. And Michael has been going back and forth over the last week, and I think we're pretty lucky to have his expertise here, and even more so to basically have a one-on-one mentoring session, which is fantastic. So with that, Michael, please take it away, and I'll be right here hanging out as well. So any questions you have for me, I am just going off camera to free up the bandwidth.
Yeah, sounds good. Thanks, Joey. And yeah, like I said, Samantha, since it's just, if there's anything in particular you want to go over, I mean, I have a bunch of slides here, I'll probably breeze through some of it, but if we want to spend more time in one area, we can definitely do that. And we'll keep it informal. I was going to intro GluMac, but I feel like, it's a bit preachy now if it's just one-on-one. But yeah, we've been around for a while. We were acquired in 2017 by a company called Tetra Tech, and it's really opened the doors and opportunities for us to work on more projects on a more national and global perspective. We still operate as our own operating unit, and individually we're located predominantly on the West Coast, and we have also an office in Austin and what we call our national office, which is for pretty much spawned out of COVID for employees that are not really near a brick and mortar location. As far as services we provide, we're predominantly an MEP engineering, design engineering consulting firm, but we do have groups that work on other things. Our energy group, which I'm a part of, is about 25 people throughout the West Coast predominantly. We have sustainability consulting, commissioning, lighting design, low voltage technology, as well as some other specialty services. And highlighting kind of our sustainability within our project portfolio, we pride ourselves in bringing sustainability into every project we work on, regardless if there's sustainability goals or not. Cost-effective sustainability solutions. But here's a couple just numbers of some of our projects that do pursue those certifications, various ones, predominantly LEED and WELL. And wanted to throw this slide in here. This is just highlighting some of our electrified projects, predominantly in Washington, Oregon, and California. There's a couple here, I think, in Texas and one in Oklahoma, but kind of throughout our portfolio. And this probably hasn't been updated in about a year, so it's a growing list, obviously, especially in California, where a lot of our cities have electrification requirements. Just to talk about some of the learning objectives, this is like an AIA accredited course, and I think CU through professional engineering and all those types of different organizations. So if you do need any credit, just shoot your AIA or other number within the chat, and we'll make sure that we log that and get you credit for that. But really want to learn what decarbonization is. Sounds like I might be preaching to the choir a little bit, but kind of go over what's driving decarbonization, electrification in different areas, and we'll probably hone in predominantly in California, and I'll try to stick close to Sacramento. Really understand what are the tools to get to electrification decarbonization. There's a lot of ways you can get there for a lot of our systems that do use natural gas traditionally. So what are the systems that make sense, and what are the efficiencies and kind of the pros and cons of those systems? And talk a little bit about design applications. So specifically, what are the main differences in an electrified option compared to a traditional natural gas option for heating systems, domestic hot water systems? We won't dive in too much on cooking or clothes dryers, just because they're pretty similar in size, other than the distribution of infrastructure of electricity to go into those machines. But we'll predominantly stick on central heating and domestic hot water systems. And just some descriptions of electrification. Seems like I probably don't need to go through this, but maybe I won't now. There's another slide that goes over better than just some words on the screen, so I'll jump through. And really looking at the total picture of carbon within our, not even just our built environment really, but just globally how we're using energy, right? A big portion of that is going to be within our building footprint, and those more traditional or historical natural gas systems that serve heating for buildings, whether they're furnaces or they're developing heating hot water through a boiler or a water heater, um, and domestic hot water systems. So systems serving showers, dishwashers, sinks, things like that for occupant usage. And really, we're going to be honing in on this area. There's obviously a lot of other areas that are contributing to carbonization within our planet. And there's other factors and other things going into these other areas that are generating CO2 emissions. Transportation more recently and kind of notably is, especially California has a 2035 goal to be 100% of new vehicles be sold, be fully electric. We know Senate Bill 100 is contributing to decarbonizing our electrical grid, and there's some other pieces of that pie that are going to be addressed and worked on, I'm sure, within the next 20 years, but we won't focus on those in this conversation. So how do we actually decarbonize? And kind of backing out at the utility level, so not really looking within the building, but further back. And I mentioned that Senate Bill 100, which we'll go into a little bit more detail later. But um, historically we use coal, a lot of coal and dirty power generating systems that are distributed across the country and across the state. And it's pretty dirty to generate that electricity. We know that the emissions are known for that. And a big crutch towards this decarbonization move has been natural gas systems, which the state heavily relies on natural gas to develop pretty much consistent energy, electricity through the state. And we know that renewables, other than the embodied footprint of some of the materials and transportation of those materials, it's a renewable resource. So it's not taking away from any of the finite resources on the planet to generate that electricity after it's developed, after it's constructed and put in place. We know that our natural gas infrastructure is deteriorating. There's a lot of studies on this showing some of the predicted or estimated leakage rates across the state, across the country. These are very tough to figure out because a lot of leakage is not noticed. It's not reported. It's kind of in small quantities, but when you add up those small quantities across an entire nation, it can really be a significant emission of both methane, CO2, and other greenhouse gas emissions. So this is just highlighting some of the areas in California. This is a national list of the top 10, I think. Looks like there's more than 10, but a lot of those are California. A lot of those are our infrastructure, whether it's SDG&E, PG&E, SoCal Gas territory, or municipality-owned utility. We do know that there's a lot of leakage, both on the customer side behind the meter and in front of the meter. So really, this is a growing problem that is only going to grow further and further as we as our infrastructure ages, right? And just one more comment on the leakage component. There's a pretty cool, I guess it's not cool, it's probably not the best word for it, but a pretty interesting article on methane leakage in buildings and some crazy thermal infrared cameras that catch some of this leakage within buildings and really showcase or highlight some of the specific areas that are seeing significant amounts of leakage, predominantly in the industrial, chemical storage, things like that, areas within the state. And unfortunately, a lot of these leaks in these buildings are located in areas that are socioeconomically disadvantaged. So it's really a magnifying problem in areas that it shouldn't be. Talk a little bit about where our utilities are. Again, we're going to focus in on the state of California. And you can see that from this graph, some of the composition of our electricity. Where is our electricity coming from? Whether it's a renewable resource, nuclear, natural gas, coal, or other. Other is, I guess I won't dive too much into other, but other is a pretty tricky piece where the actual energy credits are not really known, and they're coming from they're being transmitted from other outside with the California ISO grid. So sometimes it's not fully known what those are. They could be very dirty. They could be pretty clean. But you could see that's only a significant composition of some of our utilities, predominantly in the southern region of California. But we know that and this is a little bit dated, so this is 2018. There's some newer power mixes I should update this slide for. But we know by 2045, Senate Bill 100, which is passed into law, requires all utilities within the state, to have 100% of their electricity come from renewable resources. There's different parts in time within I think one's 2030, 2035, 2040. There's certain goals, thresholds that the state is, I don't think it's required, but desiring the utilities to be at within those areas. And I'm pretty sure like PG&E right now is close to 40%, similar with SDG&E and SoCal Edison. LEDWP, which you'll see, is a pretty large municipality-owned utility company, and still has a pretty big portion of coal. And that's surprising, right? Because we don't have any coal plants in the state. But within the LA basin, it's pretty tough. There's a lot of people, a lot of electricity being used, especially in those dirty times of the year. So a lot of that power is actually transmitted across the border from Nevada and Arizona. And that's why LEDWP actually is one of the dirtier grids in the state. So figuring out how we generate consistent electricity when it's needed, at the time of use it's needed, is going to be crucial in the state meeting this 2045 goal. A little bit more just on the power mix, and showing really the offset between the losses you incur from generating electricity renewably somewhere far away, with all the transmission losses, all the step down losses, all the things that happen to that electricity, that amperage, before it gets to your building, compared to just getting natural gas burning on site and generating heating, or maybe a cogen plant using other things for that actual natural gas combustion on site. And what we found is, in California, this is California wide, so various utilities, this graph looks a little bit different, right? It looks a little bit worse for DWP, it looks a little bit better for SMUD. But you can see about 2020, 2019 was the time that it was more efficient holistically from a source energy perspective to bring that electricity, have losses through transition infrastructure, step down losses through transformers, those types of things. It's more efficient in terms of greenhouse gas emissions, CO2 emissions, than burning gas on site, which we know burning gas on site is probably about an 80%, 90% efficiency for heating. But there was kind of a step over where before then, our electricity was still pretty dirty in how it was comprised, what it was comprised of. So it actually didn't make sense from a holistic point of view. But we know that that's changing, and that will continue to decrease as we hit net zero, or zero emissions associated with our grid. Here's some more information just on specific utilities. I probably should have showcased SMUD, so sorry for that, Joey. But you guys are up with the punch with these. But different targets, individual utilities are setting their requirements individually, so not really enforced by an entity like the CPUC, but really setting targets for themselves to meet some of these thresholds in order to get to where they need to be, where they know they need to be by 2045. And then we know there's some other state policies, right, outside of the full electrification required for, or full renewable resources required for utility electricity. We know that there's the energy code, which is a very fun thing to be involved with, especially as it changes every 3 years in interesting ways. We know that sometimes that energy code does not fully align with the electrification goals of the state. So there's some nuances there, and there's some work between agencies that's required from the CEC, from CARB, and from the CPUC to make sure that everybody's moving in the right direction as we enforce new codes, as we enforce new requirements on owners and utilities, to make sure that everybody's aligned and moving forward and what the goals are. And talked a little bit already about Senate Bill 100, but just on that fully renewable resource source energy for electrical utilities in the state. Additionally, there's some cities or local AHJs that have electrification requirements within their districts. So they can be known as reach codes. They can be individual city planning policies that are approved, and they've gone through a various. There's various ways that these have been enforced within cities, but there's a lot of cities now, and this list is growing and growing of cities that require full electrification. City of LA just passed it this year. Any building after April, I think it was 21st, or permitted after April 21st, is required to be fully electric for heating and domestic hot water systems. There are some exceptions. City of San Diego has in their climate action plan that they're going to be enforcing that this year. Hasn't come out yet, but a lot of big cities and a lot of other cities are following. And that's requiring electrification, some exceptions, but requiring electrification for a lot of these major central systems within commercial buildings and residential buildings. Additionally, some cities are requiring electrification targets or goals or implementations for existing buildings. We know that this is going to be challenging, especially for buildings that are in climate zones that are colder, in utility areas that have already pretty stretched thin grids, and circuit linings, and buildings that are high rise or in very dense urban environments that don't have a lot of space to throw these larger pieces of electrified equipment. We'll talk a little bit about the space differences between electrified equipment compared to natural gas equipment later, but we know that this is going to be a challenge. And we know it's especially going to be a challenge as these utilities are forced to increase their service lines, increase their voltages, their amperage through different areas, especially dense urban areas, to meet all these electrification requirements, all the electrification of our transportation requirements, all while hitting fully renewable resources by 2045. This is a big challenge, and it's a big pile that keeps getting added to that you now have to change that pile to fully renewable. So it's a continuously growing, I won't call it a problem, opportunity for our state and our utilities to figure out how we're going to do it. Because to be honest, we're the first state to do it at this large of scale for both new construction and existing buildings. So it'll be a fun next 20 years for all of us, I think. Some of the opportunities in renewables, when we say renewables, typically the first thing that comes to most people's minds is solar PV, which is pretty fair in our climate and in our state. It's definitely a higher performing or a higher generating renewable resource that's able to be small scale within our commercial and our residential properties. This is just showing some of the cost differences. This is only showing 8 years, but how those installed solar PV costs have reduced over time. And a lot of this was stemmed by different FTIC or solar investment tax credits, different federal and state tax credits. There still are some through the IRA and the FITC, but a lot of that stemmed into companies creating this technology that's more efficient and cheaper to develop. And no electrification presentation would be complete in California if we didn't mention the duck curve. So wanted to highlight this and some of the challenges that our state's going to have. And this is from a very short-term perspective. I'm going to show, my next slide will be a little bit more long-term perspective. But from a short-term perspective, we know that the sun comes out during the day. We know that we actually curtail a good amount of our solar in the state, which I'll talk about on the next slide. But when the sun goes down, our demand doesn't. Our demand actually goes up overall from a net perspective. And a lot of that's because you can see this graph on the left. This is from, and you could pull this for any day of the year. You can even pull it for today if you want, with the predicted values on a CAISO website, California ISO website. But this, excuse me, this teal bar shows our net, our total draw, our total demand pulled through the state in megawatts. This purple shows our total demand met. That's net without renewables. So everything in between the purple and the teal is provided by renewables. You can see some overnight stuff that's wind and hydro and geothermal. But you can see that this is really what we're trying to tackle here. This huge peak when the sun goes down, people are still in their offices, people are heading home, people are going to restaurants, people's air conditioners and all these things are on. You can see this is really the problem child that California has, that California needs to address, right? And you can see this increased ramp in our predictive, our predictions in the next, I'm sure this is going down and down. This ramp up requiring us to turn on our natural gas plants 3 hours early and to handle that load at that later time of the day, that's really the dirtiest energy that we could possibly have. And that's where a lot of solutions are going to come into play, like short-term energy storage, whether that's thermal or battery, demand response, behavior change within all of us, right? We see our utility rates are now more expensive 4 to 9 p.m. Hey, let's run. Historically we always didn't want to turn our dishwasher on at noon. Now you really want to. That's the cleanest power you can use at that time of use. So it's changing how we see our grid and how we use energy individually. And just kind of stepping back a little bit, I talked about the curtailment. California, I think every month now, breaks its own record, which is how much solar PV it actually curtails. So that's just shut off because the grid is in fluctuation. We don't have the demand that we need to backfeed to net meter that solar back into the grid. Not a great record to break all the time, right? We don't really want to break that record. We want to store that energy in other ways, whether it's battery storage, it's potential energy storage, it's thermal storage, other ways that we can store that energy to use later on to really maximize our time of use offsets, right? And this shows just kind of a more curtailment by the hour within different months. So, it's really those cold months that it's still pretty clear outside. It's not rainy and not cloudy. And it's not super hot, so our air conditioner's on. We're not pulling a bunch of energy at 3 p.m., but we have all this power that we don't know what to do with, right? So it's really it's something that our state's going to have to solve really within the next, by the time we want fully renewable electricity by 2045. And I saw another folk just jumped on. Just FYI, you can raise your hand or jump in with any questions at any time. This is definitely more of an informal presentation. So why do we want to electrify? And easy answer, because our electricity as a form of energy can be decarbonized, right? We talked about Senate Bill 100. We talked about the portion of renewables that are already comprised, that already are a portion of our total electricity within the state. And we know that combustion cannot be decarbonized, right? You can do it at a certain extent. You can use biofuels or other cleaner sources for combustion, but at the end of the day, it's still combustion. So that's really the main draw for why we're trying to electrify our systems, why the state is pushing so hard from different avenues, whether it's the CEC from CARB, from the CPUC on utilizing electricity for these traditional gas-fired systems. And CARB is obviously interested from another reason, from air quality perspective. And that's the same, similar for both the built environment and the transportation sector as well. So we talked about this graph. I should reorganize these, but we talked about this graph, kind of the offset of when is the, from a holistic point of view, when is the net greenhouse gas emissions lower for electricity usage than natural gas. That happened about 2019 from a statewide perspective. From a DWP perspective, it's actually not predicted until about 2026. The main reason there, again, going back, is the amount of, other composition of our electricity in Los Angeles, LADWP. There's a big amount of coal that's coming from across state lines. There's a big portion of natural gas. And that's really probably a factor of the LA basin and how tight it is compared to how much renewables are actually online within that basin. You can see right now, there's a switch over here in about 2026 that's going to say, hey, now it actually makes more sense from a greenhouse gas emissions perspective, to use electricity rather than gas. This is good to know. It's informative, but it shouldn't be driving our decision making in not electrifying systems now. Why? Because if we invest all of our capital infrastructure costs on a new construction projects or an existing building project to keep those natural gas systems online or put them in because it is, lower natural gas now, it's going to cost a lot of money and probably not make financial sense to take that equipment out before its end of life, right? Within 3 years and say, hey, we're going to put in electrified equipment now. There's a lot of other factors that we need to take into account when we do think about which systems we're going to put into a building from a new construction standpoint, or renovated or retrofitted systems for an existing building. This is a graph that shows if you use these systems, right, either electric resistance, an air source heat pump, which has about an efficiency of a COP of 3 or 300% efficiency, a heat recovery chiller with about a 600% efficiency that's generating both heating and cooling. This shows what's your actual emissions savings in reducing that electricity now compared to the life of that piece of equipment. That piece of equipment will live about 20 to 25 years probably more for electric resistance. But you could see a lot of that benefit you're going to be seeing early on because of the composition of our electricity within the state. And eventually you're still going to use a lot more electricity in the end. So, if this was just electricity usage, these lines would be even. So you're still going to be paying a lot more for electric resistance systems in the end. But when our grid is fully comprised of renewable generated electricity, those emissions will be net zero, right? They'll be the same because the utilities are required to meet that requirement. Some of the people that are electrifying that we work with, that GluMac works with, pretty much everyone's electrifying, right? And a lot of these cities I talked about that already have electrification mandates. But a ton of public agencies, a ton of private agencies, DGS, which has a ton of buildings out in SMUD territory, UC system, the CSU system, right? Sacramento State. All of these entities are electrifying now, regardless of the city, wherever their buildings physically located requirements. So that's exciting to see, and exciting to see pioneers leading that, so that it's making technology, it's making the systems that we're using more cost effective, right, for our contractors and subcontractors getting more familiar with installing and designing those systems. And it's bringing that technology, similar to how I showed that solar PV graph of cost per watt. The technology is getting more efficient. It's getting cheaper. They're producing more of it. So it's helping that overall direction of the state and the country, frankly. I've been belting for 30 minutes. Any questions on that stuff? Anything I went over? We're kind of going to dive a little bit more into specific systems from a mechanical, electrical, plumbing perspective for electrified options. But I'm going to take a break, 1, to breathe, and 2, to ask if there's any questions before we kind of divert on topics a tiny bit.
Well, it was great. Thank you.
Yep, perfect.
And Michael,
Okay.
I have a question. I know
for it.
how it is to be on the utility side of this a little bit more, but from an outsider's perspective, a lot of these zero carbon, zero emissions goals are defining it as though all of the power is coming from within the state of California. Yet the reality is there's, I think, 14 states and British Columbia on the WAC. They're all contributing to the stability, reliability, and generation mix on the grid. What is your perspective on why California is so focused on all of the generation coming from within the borders of California? Or it seems like that's where the onus is anyway.
Yeah, that's a good question. I just wanted to pull this up on the side. When what Joey's talking about is kind of our grid operators, and they're broken out. California is a pretty tightened one, but a lot of our states are sharing power the picture I showed earlier, which I'll jump back to just to answer that, is I'll just show this one. This is going to be a big factor that in the next 22 years, right, the state of California is going to have to figure out what is other. Other is comprised of electricity that it's difficult to know where it came from. Right now, it's just a commodity that's transferring in tariffs, and it's hard to actually know where that's coming from, what it was comprised of, what utility plant it came from, what state it came from in some cases. And it's lost all of its attached details, comments. It's lost all of its attached identity. It's just electricity. That's all it is. So the state can have fully renewable electricity coming from other states as well. We have these grid operators trade electricity back and forth all the time. But we need to align these details. We need to keep that generation commodity with that identified electricity so that it can be allocated to a renewable resource, a dirty resource, coal, natural gas. It can be aligned with where it came from, right? If our electricity is coming from somewhere way over here, we want to know that, because there's a lot of transmission losses that are associated with pulling that electricity from here to here. And all of those factors are going to be a lot more important, and we're going to have to understand from a state perspective, if we want to hit 100% renewable, it's not going to make sense to do that looking at Cal ISO's grid only. It's going to make sense to identify those resources and allocate them across the grid operators so that the rest of the country can follow, right? It'd be really cool for fully net zero by 2045. We're going to be, right? That's what the state's doing. But it'd be even cooler if the rest of the country follows suit and they have a pathway and a mechanism to do that. So really, it's about setting the tone. And I think, this other factor, and you can look up, I won't spend too much time, but if you look up the California utility, what's it called? Power content label, I think it's called. So you can see every utility every year. So let's see, let's go to 2021 and let's pick on SMUD. You can see what their electricity is comprised of, and you can see what is that. Where does that land compared to California wide? Where does that land compared to the different rates that they offer? Right, they have a fully renewable rate that you can purchase. So you can zoom in here. I'll just spend one more minute here. And you can see what portion of renewable. It looks like their general mix is about 30%. So no matter what, when you're getting electricity from SMUD, at a minimum, it's about 30% renewables coming from renewable resources. They have some other options that you can choose to get fully renewable electricity, right? You can get it from their SMUD Solar Shares program, which DGS is an avid partner of. And then it relates it to the power mix across the state. You can see, oh, we're not doing as good, right? Okay, maybe not, but let's look at coal. That's pretty much the dirtiest thing you can use, right? A lot more there. You have a lot more hydro, right, in SMUD territory, a lot less statewide. So you can kind of see where your building is within what utility it's in, and kind of understand from there. But I know it kind of went 5 different ways to answer that question, hopefully answered, but there's a lot of factors. It's not easy for the utilities. It's not easy for the California ISO grid operator. It's not easy for individual buildings, but we're all going the right direction. We all need to be communicative and transparent with each other and how we're getting to where we need to be.
Thanks for touching on that, Michael. Appreciate it.
Yeah, of course. So now we'll jump into some specific design considerations, and really honing in on the central systems I talked about, predominantly heating, domestic hot water. We're not going to talk so much on induction cooking, heat pump dryers. Those things are kind of understood. I'm sure there's another hour-long presentation we can do on those, but we're kind of stick to those central systems, typically the systems that are behind the scenes that you don't really notice as just an occupant of a normal building, right? You don't see the boiler, you don't see the heat pump. You feel hot air, you feel cold air, but you don't really see what's generating that. So we're going to talk about some of those systems now. And looking at a traditional building design, I keep saying traditional or historical gas-fired systems, right? What does that mean? We all know what that means, but traditionally they've always been gas-fired, right? Because we haven't had significant pushes from a climate change perspective on electrifying those pieces of equipment, because gas is cheap when you compare it to electricity at a per BTU level, at an energy level. But a traditional building, hopefully you're coming from renewables, but you come from a natural gas power plant. You run your air conditioner, that handles your cooling load. You could probably exactly mirror this for your domestic hot water heating load. So we'll just add that as domestic hot water, but you're pulling natural gas from somewhere, right? Storing it, you're distributing it across the state. It's going into your boilers or your water heaters, and you're generating your heating system or your domestic hot water heating. When I say domestic hot water heating, I mean showers, sinks, dishwashers, things that people use, occupants use for their personal usage rather than using to heat air through a building. What's an electrified building look like? So this could be a multitude of things, not just a heat recovery chiller. But you're using electricity to generate both cooling and heating and domestic hot water heating for your building, right? And that's really the main difference, at least dialed down to a simple sentence. You're using electricity to handle all the loads in your building. You're not using gas for anything. So I wanted to break down the electrification, right? Big, cool word. What does it actually mean? Because there's a lot of ways to get there. And wanted to break it down in terms of tiers of what we say tier 0, tier 1, tier 2, and tier 3. And really just talking about the differences in efficiencies. And we'll talk a little bit about why you would choose one over the other. Obviously, we should choose tier 3 for everything, right? But it's expensive, but it might not make sense for your climate, but it might not make sense from an overall greenhouse gas emission standpoint. So we'll talk about some of those differences and why you would choose systems over one tier over another tier in certain cases. And if there's any questions on this, definitely just raise your hand or unmute yourself. But from a tier 0, we'll talk a little bit about electric resistance. And I'm just going to intro these because I think they're on each of these slides. Electric resistance, VRF or air heat pump technology. Hydronic heat pumps, that's an air to water heat pump that's pulling heat, extracting heat from the atmosphere or the air, generating hot water and pushing that hot water through a building or to your domestic hot water systems. And the tier 3, the last one, is a ground source system. So using geothermal energy, energy within the earth, right? The temperature of the earth is a lot more stable and constant through all of our lifetimes and through the planet's existence, rather than the temperature of outside air. So using that ground as a way to extract heat and use it for your building is a lot more efficient. And we'll talk about those efficiency differences here. So electric resistance. Generally negative connotation, right? Electric resistance, you can think of it as a toaster coil, just with an airstream going through it. All it is you're heating up some copper wires, some conduit, you're heating it up really hot and you're blowing air past it. Same thing with an electric boiler. You're heating up coils that are tightly wound and just have a lot of current going through them, and you're pushing water right past them. It's about 100% or 99% efficient, which sounds great. But in reality, they use a ton of electricity. Electricity is expensive. We know that. And there's other options that are a lot more efficient. We'll talk about those next. But this is kind of the base level electrification. Like, oh, I need to electrify this furnace in my house. How do I do it? You could throw in electric resistance. You might have to upgrade your service breaker. You might have to, it might actually be a lot more expensive to run that rather than your furnace, just because of the price per BTU of gas compared to electricity. But it is an option for electrification. The next one is VRF, or even split systems, air to air heat pumps. So this is what would be an electrified version of even a house air conditioner and a house heat pump, right? You have an outdoor condensing unit. It has refrigerant lines towards an indoor fan coil unit. and it's pushing either hot refrigerant or cold refrigerant that fan coil is blowing air past. All it is it's using refrigerant as the mechanism to move, to transfer heat, pulling heat from outside, putting it inside. That's all an air-to-air heat pump is. And so it's probably about 2 to 3, sometimes more, times more efficient than electric resistance. So about 200% to 300% to 400%, somewhere in there. Really depends on your climate, right? If you're up in Arcata, it is cold all the time, and that thing is not, it's really hard to pull heat out of cold air. You can do it. You can do it in 0-degree weather. You can do it in some pretty crazy areas in the country. Luckily, I'm sure there's some areas in California that experience this, but hopefully nobody on this call and nobody listening to this. But it's a lot more energy intensive to pull heat out of that from an outside air perspective. It really depends on your climate that you're in. In a hot climate, it can be maybe 400% efficient. And when I say 400%, that's a 4 COP. So a COP, I'm just multiplying that by 100, and that gives us about the percentage of efficiency. So these systems, and I have a graph later that shows the COP differences that I'll jump to, but shows some of those efficiencies. Let me jump to here just so I can get through these. The hydronic heat pump, very similar of this system, except instead of transporting refrigerant inside the building and running that through a fan coil, all of that entire system is going to be located and centralized, probably on a rooftop somewhere, maybe outside or maybe in a basement, as long as it has airflow. And it's going to generate, the refrigeration cycle is all inside that kind of unitized system, and it's generating hot water, and it's pushing that hot water through the building, pushing hot water over here. And same thing, you're just running air over those coils. The coils are filled with hot water, and that's how you're getting heating for those systems. And this still uses air source. So it's still using the atmosphere, the outside air temperature, to extract heat, to pull heat and give heat to the building. All you're doing with any of these types of refrigeration systems is moving heat from one place to another. That's all it's doing. It's the same exact thing as an air conditioner, except working in reverse. And a cool analogy I actually heard 2 weeks ago, which I'll share just because I really, really enjoyed it, and it really put things in perspective for me. A really cold climate, let's say we're up north in Minnesota, and we have a heat pump, and we want to keep the building at 70 degrees, right? And it's 0 degrees outside. That's a 70-degree temperature difference. It's really, really big temperature difference, right? It's hard to pull heat out of 0-degree air and keep a 70-degree building warm. Very similarly, if you look at a grocery store here in California, right? Let's talk about Sacramento. And I know it's been hot the past few months. Luckily, it's cooling off now. 100 degrees outside. You need that fridge at 40 degrees. That's let's just say 30 degrees. You have a freezer in that grocery store. That's the same temperature difference, 70 degrees, 100 degrees to 30 degrees. The compressor, the thing that's doing the work, doesn't care which side's which. It's the same problem that thing is solving. It's saying, hey, I have a big temperature difference. It's really hard for me to push heat into this 100-degree air. So I have to work a lot harder to do that to keep this thing 30 degrees. So it's the same problem the compressor is solving, and the efficiencies that are associated are aligned with that outside air condition. So that's a cool analogy that I heard that kind of helps paint that picture. Tier 2, this is continued on that. I see I only have 10 minutes left, so I'm going to brush through some of this, just talking a little bit more about hydronic heat pumps and what types of options there are. There's heat recovery options, which generate simultaneous heating and cooling. They have increased efficiency when you're generating both. They do not have increased efficiency when you're generating only heating and no cooling. It really needs to be simultaneous. So that's the key with these heat recovery systems. And the tier 3, which is that ground source. This is using the ground as a source of heat. Ground temperatures in the state range from 60 to 70 degrees. So you can think about it in the winter, in December, when it's really cold in Sacramento, it's 30, 40 degrees outside. That same air source piece of equipment could be operating a lot less efficiently than if you had 60 or 70 degree water as the heat source, right? It's operating a lot more efficiently. There's a way less temperature delta lift that your compressor needs to do in order to get you heating. And here's kind of an efficiency comparison just on a chart, a very simple chart. Gas boiler operates at about 90% efficiency, maybe a little bit less. Electric resistance about 100%. That VRF or heat pump or air source we talked about is anywhere from 2 to 4-ish, depending on your climate. And a water source system is anywhere from 5 to 7. So now we're going to get into the fun stuff. I'm actually going to skip. Another factor of electrification that we're not going to talk about today, except for this single slide, is refrigerant, which is a growing it is a growing thing in our state and our country now, of refrigerant leakage and how bad refrigerant can be for the environment, and finding better refrigerants that cause less ozone depletion potential or a global warming potential. So there's a couple other factors that are associated with these electrified pieces of equipment that have refrigeration cycles. That's another factor to keep in mind. And this is a growing topic that you'll hear more and more about within the next 5 or 10 years as refrigerants get phased out in the state and within the country. This could be a whole nother hour presentation, so I'm going to jump off it before I get questions. I'll talk about these. So here, a few of these are going to show some cool dashboards, which we develop internally at GluMac. But I'm going to talk about this, and I'm going to jump through these 2 slides to really talk about this for a couple minutes here. And this is a project we looked at a campus. This is in Southern California for a campus, educational, higher education building campus. And what you could see is this building, this campus load was sized at about 50,000 kBTU. Sorry, 50,000 kBTU annually. So that's the peak load. That's the mechanical engineer saying, hey, if all the buildings are empty and they need to be 70 degrees, and we need this and this and this, and it's the coldest day and the sun's down, that's what we need. Okay, got it. We know when we energy model and we actually take into account diversities and load factors and different things going on in these buildings, we know that we're probably only going to be, sometimes it's up to here, but we're only going to be 50 to 70% of that peak load that's calculated by the mechanical engineer. That's okay, right? They need to be able to handle the worst condition, the worst day. They need to handle that. Otherwise, there's other things that are going on, right? You're not going to have a happy owner when that 1 hour happens out of the entire year. But we know if we break down the year in hours, this is just number of hours. That's all this is. So combined, this is 8,760 hours. We know that a lot of those hours, especially in California, where we have a pretty nice climate in most of our areas, most of those hours are going to be pretty low conditions, pretty low heating conditions. And what this is really showing is we can right size our systems so that we can handle the most amount of hours efficiently, and we can handle the other ones maybe less efficiently. Maybe it's going to take more money. Maybe it's going to cost more from an electricity perspective. But it's going to take up less space. That equipment's not as expensive. And there's a balance between cost effectiveness and overall energy efficient and electrified design. And this is really just showing the percent of hours, right, below 6,000. So if we're talking right here, this is right where I drew that line. 50% of the hours are in, 50% of the hours of the year are in that load condition. You could save 30% of the gas, 30% of the greenhouse gas emissions associated with your entire heating system if you just handle 10% of that plant size, right? If you handle the first 10% with a nice electrified, efficient design, you're cutting out 30%. And obviously, as this increases, if you're looking at higher numbers, when you start to pick a place in the sand where you draw that line and say, okay, I want an efficient electrified design here, and for the rest, I want electric resistance booster boilers, which aren't efficient, they're expensive to operate, they're going to increase my demand, my utility costs, but hey, that piece of equipment is this small compared to this big, and it's a lot more cost effective right now to buy that. There's certain evaluations you can do from an energy modeling perspective where we can identify what makes sense for your project and your climate. And this just shows another tool that we've used to help paint that picture and understand what doesn't work. Okay. I'll try and update that link when this goes out. But looking at especially when you incorporate domestic hot water heating in a system, you can really find out where that heat recovery load is. I'll go up to here. You can find out where you can right size that heat recovery chiller to operate super efficiently. And then you need some other systems, right? You maybe need an independent chiller to handle that peak cooling load. You maybe need an independent heat pump to handle that heating load. But you can handle a lot of it through the year because there's simultaneous heating and cooling that we talked about. That's important for those systems to operate efficiently. All right, 5 minutes. I'm going to brush through this. Let's see what I got. Okay. So design considerations. This is going to be a little bit clunky, but mainly mechanical and plumbing focused. Historically, we've used 180 degree and 140 degree return for our heating hot water systems or domestic hot water systems. We really want those temperatures to be lower. The heat pump technology operates a lot more efficiently when it's at that lower temperature. Some heat pump technology can't even get to that 180. So it really is a factor how you're building. If you have an existing building that's sized, all the coils are sized for 180 degree temperature water. It's really hard to meet that with an efficient and non-expensive heat pump option. So supply of water temperatures is big. Sorry, I'm seeing some notes in the chat. Your delta T is important. You know, we're talking about, we don't want it to be 40 or 50 degrees like we see in most commercial buildings. We want it to be somewhere between 10 and 30 is really where you want it to be. The size of this equipment is a lot bigger than our traditional natural gas boilers that we just lay out somewhere, right? Takes up a lot more space. It requires a ton of airflow. You can't just lock it in a closet somewhere. You need a good amount of airflow for this to be able to extract that heat we talked about. So they're similar size to a chiller. And they're big machines and they're expensive machines. I think I have another slide on cost. They're big and expensive, and they require some other pieces, other bits and pieces that take up space and cost money, right? Some buffer tanks, they require different type, sometimes additional things within the infrastructure and distribution to account for that. So it's something to be aware of. Space planning, this is just an example, but you know, this type of system serving about a 200,000 square foot academic building required about 5,000 square feet of mechanical roof area for the air side and the heating systems, the heat pump systems. So just some, and this is just an example, but it takes up more space, right? It's going to take up more of your roof program or site program if it's at grade. And a few minutes left. Design challenges, potential higher first costs. We talked about that. There are limitations with existing buildings, especially existing buildings that have a set electrical capacity of their service, and they're in dense urban environments where it's really hard to put that equipment outside, right? Operational costs right now, electricity is about 6 times more expensive than natural gas at a per BTU level. It might be lower now with all the things going on with natural gas, but five times maybe, let's call it 5. This means that your electrified option has to be 5 times more efficient at a minimum to cost the same. Tough to do. That's going to change. We know that utility rates are changing both for electricity and natural gas, but something to keep in mind. It's not necessarily going to save you money on day one. These equipment are hard to control. They require a lot of commissioning and testing, space allocation, and this is changing now every day. But you know, our industry, our subcontractors are more familiar with natural gas systems. Again, this is shifting, but it takes time, and it takes those thought leaders like DGS, SMUD, the CSU system, and other electrification-driven companies to lead that charge. Some of the major benefits, future policy, right? We know electrification policy and requirements are coming down the line, both on a state, a local, a county, an individual perspective. Air quality improvement, there's no combustion on site. They're safer. You know, natural gas is obviously has its own has its caveats for safety and explosion and fire prevention. You know, preventing natural gas excavation in the areas and the communities that it exists in is a big factor. It's not necessarily aligned with where your building's at, but it helps, you know, somebody else that's living in those areas. And it's a global trend. It's not just, we're not doing this only in California. We're doing it globally. I'm going to skip this and just go to key takeaways since I'm at 1 minute left. Here's the key takeaways: right size your systems, right? We do not want to throw in heat recovery equipment that's expensive, takes up a lot of space. If you don't have the loads that make it make sense, right? We want those systems to be rightly sized to handle those loads for it to be a cost-effective electrification solution. Right size your equipment. Understanding your loads, understanding your annual load profiles is really helpful in making sure that you're making the right decisions. Future proofing now. So even if you don't have electrified systems today for your new construction project, make sure your electrical service capacity is sized correctly so that you can swap out that natural gas equipment for electrified equipment later. Make sure those temperature differences, right? The delta T, the supply temperature of your heating hot water system, is sized appropriately so that when you do electrify that piece of equipment, you don't have to rip up all the infrastructure, all the piping through the building. You can use the same piping and just just swap out the boiler for the electric heat pump. Resilience is another component, right? Natural gas. Over the next 10 to 20 years, we're going to see interesting things with natural gas, right? There's going to be a decrease in purchase and using. That means that the cost for that natural gas is going to be a lot more per BTU because you're going to have to pay for that infrastructure upgrades and maintenance with less general natural gas usage. And really, full circle, combining it to a grid interactive building. All the things we talked about for time of use electricity, our buildings need to respond to our grids. It's going to be very important from a time of use perspective, and it's going to make financial sense for your building to be able to respond to SMUD saying, hey, there is an issue with our power, reduce energy usage right now, and our grid doesn't go blackout, right? There's going to be financial incentives. There's going to be a lot of other things that are going to benefit that. And these fully electric buildings are going to be able they have the bones and the pieces to be able to respond to those grid interactive signals or demand response signals. And with that, sorry, I went through that so quickly. Thanks everybody for hopping on. My email is down here at the bottom, madams@glumac.com. Definitely reach out for any questions. I love geeking out about this stuff and appreciate everyone's time. And I'll dish it back to you, Joey.
Thank you, Michael. Appreciate what you could cover there and getting through your presentation. Do you, and I don't want to put you on the spot, but if you're available for questions, it looks like Sabrul might still be with us here. If there are any questions, do you have a few moments left to answer anything that they may come up with?
Yeah, if you have any questions, Sabrul, just shoot them over.
And you can also always just email myself and I can chase down answers if you've got to run. Happy to support any sort of knowledge sharing that I can do in this role. I have a question for you, Michael, and one of the projects on a campus that I was working on, and confidentiality, you'll probably pick up on this, but how do you perceive TES as a solution and an alternative to battery storage, especially in the context of building electrification? And in this specific instance, it's a campus, but I wonder if it matters all that much.
Yeah, it's definitely going to be a solution. It's going to be a part of the puzzle that we're going to have to use to clean our entire state grid. And I'd say its applicability is very dependent on the building type and the load profiles, right? If you're using, and TES, it historically only was like, oh, let's talk about chill water storage. Now there's 3 types of TS that we're looking at for projects, right? We're looking at hot water storage, we're looking at chilled water storage, and we're looking at for condenser water storage, which is a new thing that we're seeing more and more, at least looking into it, or buildings or campuses looking into it. What that is lithium's expensive. These battery technologies are expensive. They're also very taxing in where they come from, how they're transported, how they're manufactured, and their lifetime, right? They require a lot of maintenance. They require a lot of different things. So there's its own factors, especially for campuses, right? A lot of these campuses we work with have finite resources for their facilities and maintenance staff. They don't have a ton of batteries on campus, so they're not familiar with them. They need to train staff up. They need to locate this equipment somewhere where it's healthy and it lasts a long time. There's a lot of factors to battery storage, especially lithium, that make it challenging for a lot of entities. And thermal energy storage is hot, room temperature, or cold water. It is not too complicated to handle those systems, right? Outside of making sure that water is cleaned and there's no growth or any type of microbial development in that water. But it's definitely a solution, and it really depends. It needs to be right size on your system, your usages, and it makes a lot of sense, right? You're still using equipment to generate that heating hot water or chilled water or condenser water. But once you store that in an efficient envelope to store that tank, right? You want to make sure you're not losing too much thermal loss through that. Shifting those cooling or heating loads for some buildings can offset 50% of that time of use, right? In office buildings at 4 to 9 p.m. when you're cranking that AC and it's hot outside and the sun is beaming in through these existing building windows that are single pane and not high quality. It is a big driver of energy efficiency to move that time of use. They're not 100% efficient, right? Thermal energy storage, neither is battery storage. You're actually going to be using more electricity over the perspective of a year, but you're moving it where it makes sense from a financial perspective and from a demand use, time of use perspective, so a greenhouse gas emissions perspective. And a lot of this equipment, a lot of these things can be controlled with utility signal or with data from the utility saying, hey, right now the grid's really clean. Run your chillers, right? Even if it's more expensive, you can have it controlled by the grid, the intensity of grid quality, right? The cleanliness of the composition of the grid. You can have it driven by by operating costs. You can say, hey, my rate's 4 to 9 p.m. I don't want to run my chiller for 1 minute. Okay, let's size your chilled water storage for this. And you're only running those pumps distributing that chilled water. So it's definitely a solution, and it's going to be a factor in a lot of, especially campus, where things are centralized and they make a lot of sense to distribute that chilled water or heating hot water.
Right on. Thanks for answering that. That's something that I'm talking about. Well, I was talking about in my former role on a large scale project. Yes, Brule, I will get the presentation over to you. So